Jack Jackson. We're going to look today at some more applications of integration, talking about total, present, and future value of an income stream. Total value, future value, present value. So let's start with a basic question. Would you rather have $1,000 today or have $1,000 5 years from now? Why? Well, there's lots of reasons why you might rather have money now than in the future, but one thing we could do if we could wait for 5 years to get the money is take the $1,000 today, and if nothing else, we could buy a 5-year CD. And then in 5 years, guess what you would have? You'd have your $1,000 you started with, plus whatever interest that CD would have earned in the meantime, and certainly you would end up with more money than $1,000 5 years from now. So for example, suppose that you could invest the $1,000 in a 5-year CD paying 3% annual interest compounded continuously. Now how much would the CD be worth at maturity? Well, think back to the way we did this in our algebra classes when we're dealing with exponential functions. Since this is a compounded continuously condition, we have the value equals P times e to the kt, where P is the present value or principal value that we're investing. K is our compound continuous rate of growth. By the way, I use K in this place, not R, because I use R for a periodic rate of growth. I use K for a continuous rate of growth. So, in any event, we plug this in. K is 0.03, P is 1,000, and that would be V of T. And then we plug in 5 for T and see that we get V of 5 is 1,000 times e to the 0.15, or approximately $1,161.83. So, if you could get the $1,000 now, if you could just buy a CD, then spend it 5 years from now, you would have not $1,000, but $1,161.83. You've earned some interest on top of your principal, and so it's better to have $1,000 now. So $1,000 we would call the present value, and the future value we would call $1,161.83. So let's work backwards now. Suppose you took the $1,000 of 5 years from now, what would be the present value of that? And of course by that we mean what value could we invest now at this rate and get and end up with $1,000 5 years from now. In other words, how much would we have to invest in a CD for it to be worth $1,000 from 5 years from now? So we're just taking that same formula. The future value is the present value times e to the kt. If you want to solve for the present value, you just divide both sides by e to the kt, or in other words, multiply both sides by e to the minus kt, and we get the present value is the future value times e to the minus kt. So in this example, the present value is $1,000. In this case, the future value, let me say it right, of $1,000 5 years from now is given. No, I said it right to begin with. The present value of $1,000 5 years from now. Let me say this: a future value of. There we go. Maybe that's better, more clear. In this example, the present value of a future value of $1,000 5 years from now is given to be present value is future value times e to the minus kt. Plug in the numbers, and well, specifically that is 5, and that works out to be $860.71. So you can try that with your calculator. Now, in other words, this is the amount we would need to invest today to end up with $1,000 5 years from now, and it's clearly less than $1,000 today. So when you're comparing things here and you're taking into account the fact that we can invest money and make it earn interest, we can use this if we could figure out what our continuous rate of growth would be on our investment. And based on that, it is based on that value of K, but assuming we know that, we can figure out future values or present values. And when you're comparing things, you either need to compare present value to present value or compare future value to future value, of course, at the same future point in time. And then you're kind of comparing like quantities, but don't try to compare a future value to a present value, because that doesn't really work out. Okay, now let's try something a little different now, or an extension of this idea. Now that was just one payment. Now suppose instead you win a lottery, and here's the choices. You can get $1 million paid in 4 equal yearly installments of $250,000 each starting now, or you're given a lump sum payment of $915,000 now. Now, assuming you can and will invest the money for 3 years, of course, most of us, if we got some money now, regardless of whether it was $250,000 or $915,000, we'd want some of it now to spend. But let's pretend that we're going to be able to invest this, and we're going to be able. Let's suppose we get a pretty good rate here. Let's suppose we can get 5.75% compounded continuously. Okay. Now we're going to ignore any effect this might have on other things such as taxes or whatever else. Okay? So which would give you the better value? Okay? So we want to compare, say, present value to present value or future value to future value. Now, since we have the $915,000 as a present value right off the bat, we don't have to do any computation for that. We can find the present value of this $1 million, which of course is going to be less than $1 million, but is it going to be more or less than $915,000? Let's see if we can figure that out. So first thing, notice that with 4 annual installments, starting at time 0, it's going to actually take 3 years for those to happen. You'll get 1 at time 0, 1 at time 1, 1 at time 2, and 1 at time 3. So it's going to take it's actually a 3-year period. So we are talking about a 3-year period, even though it is 4 annual installments. Okay, so in the lump sum option, again, the $915,000 is the present value. Now, in the case of the annuity of $250,000 a year, it's $250,000 would be invested for 3 years, another $250,000 for 2 years, another $250,000 for 1 year, and the last not invested at all. So the future value of the annuity, actually, it's going to yield a present value like this. So the future value is $250,000 times e to the, well, it's negative r 0.0575, and that's going to be invested for 3 years. So that's the part, that's the future value of the part that's going to be sitting there for the part that's going to be invested for 3 years. And there's going to be parts that's invested for 2 years, some at 1 and some at 0. And so this gives us our future, our present value of these different parts. So this one at the end is actually $250,000. That's the money today that you get at $250,000. This next one that you're going to get a year from now, you could have gotten it, whatever the present value of that is, it's going to be invested for 1 year. And what we get 2 years from now could have been gotten now and invested for 2 years, and so forth. Well, they all have a $250,000, so I'm going to factor that out front, and then using the distributive property, and then multiply out these exponents. And you see this here, and I did this on my calculator, and got $948,027.43. Now that's a present value. So if we were to take that amount of money today and invest it, okay, compound it continuously at 5.75% for 3 years, that's how much we would end up with, the same as taking the $250,000, invested in all of that for 3 years, the next $250,000 for 2 years, the next $250,000 for 1 year, and the next $250,000 just receiving it. And so that's the present value. So if we compare present value to present value, we're comparing that to the $915,000, and we see that In this particular case, the 4 annual payments actually yields a higher future value at this return rate, and you should choose the annuity. Another way to do it is compare future value to future value in both cases. Okay, so in this case, the annuity is a better return at that particular interest rate. Change the interest rate and then, or change this amount up here, and things would change a bit. Now notice that this case is what we call a discrete situation, where the money is coming in chunks. In fact, 4 discrete chunks. Now actually money in general kind of comes in chunks. I mean, at least 1 penny a chunk at a time. But if you have a very large, say a large corporation, their income might be modeled pretty well with a continuous function, even though technically it may be a discrete function. So for example, let's just say somebody has got let's say they got a bunch of soda machines, and people are putting quarters and dollars in those machines, and pennies and nickel, well, probably not pennies, but coins in those machines at all times, and they're actually coming in a chunk at a time, nickels and dimes at a time, and so forth. But if you have lots of those, it can be modeled very, very well, say with some kind of a continuous function. So let's take a look at here. Let's say we've got a bond, and it's guaranteed to pay 200 plus 25 times t dollars per year, okay, and it's going to do this for the next 10 years. So the amount it's paying is actually going up each year. Now assume the money can be invested at an interest rate of, let's say, 6.5% compounded continuously. Actually, as I'm doing these videos, that would be a super good rate right now. But let's pretend we can get that rate. What's the total value of the income stream? Now, the total value has nothing to do with this assumption of compounding the money or investing. It has nothing to do with present value or future value. It's just the total value of the income stream. And that's how much money is actually brought in. So notice we're given a flow rate, which is a derivative, in dollars per year. If you multiply that by years, we'll get dollars. We want to integrate that. And so what we're integrating is, to get the total value, we integrate from time 0 to 10 of that flow rate, dollars per year, times the years, dt, and we get that. In this case, of course, that's just a linear. It's very easy to do with finding an antiderivative, but here also you could do it in the calculator. And I get 22,500. Okay. Now, assuming there was no mistakes there, and then moving on, find the present value of this income stream. Well, the present value, you take this same integral, but you also multiply the integrand by this factor e to the minus kt. And that should have a t right there. And I do have it right there. It's an x in the calculator. And so we could do that integral. So we could just take this one, if you did it in your calculator, do second enter, and then go back and put that function in parentheses, and then times e to that power, negative kt, kx, from x from 0 to 10, or just enter it in like this, as it looks in your calculator. And you get $2,290.89. So that's the present value. Now it's actually going to bring in a total of $2,250 in income, but if we could invest some of this, we would end up okay, something's not agreeing on those two numbers. Let me go back and rework this one in the calculator. And okay, we're going to integrate from 0 to 10, and the function is 200 plus 25x, and we're going to integrate that with respect to x. Okay, there it is in the calculator. Let's see what that turns out to be. 3250. Okay, typo. Something was wrong there. So $3,250 is the total income that's brought in. But if we get $2,290 today invested over a 10-year period, will give us the same as if we invest this amount of money as it comes in and then only cash it in at the end of the 10-year period. Okay? So what is this income stream? If you had a choice between this income stream or a cash payment, what would be the fair cash payment? Well, assuming if you could actually get this rate of interest that we assumed, then this amount right down here, the $2,290.89, would be the fair amount for that income stream. Okay, what could we figure the future value of the income stream? Well, basically, you just change that integral to make that power positive, but instead of the t here, you're going to put 10 minus t. Because if you think about it, when you plug in a certain number for t here, let's say t equals 1, that's the money you're getting in year 1, basically, but that's going to be left for 9 years for the investment. So this power needs to be the total ending minus t. Okay, and if you work that out, that's $4,388.30. Okay, and I'm pretty sure that number is correct. I just worked that one out on my calculator just a minute ago. So note that the present value of $2,290.89 invested at 6.5% compounded continuously will return this same future value. In fact, this is maybe an easier way to compute that number. Would be this way right here. Just take that present value times e to the 0.065 times 10, and that's the same value, or you can use that as a check. So if you already have the present value, this would be an easier way to compute. Okay, let's do 2 more problems. Let's see here. All right, the value of good wine increases with age. So if you're a wine dealer, you have the problem of deciding whether to sell your wine right now, get that money now, at P dollars a bottle, or to sell it later at a higher price. Now, suppose you know the price of your wine T years from now is well approximated by this formula, P times parentheses 1 plus 18 times the square root of T. That's an increasing function, and so that's going to give you the value in the future. What's the best time to sell your wine? Now let's assume we can get a 5.75% return on investments of capital. So if we were to invest this money, we're going to figure that in as well. Okay. Now, if you think about it this way, this is an increasing function. The later you hold on to it, the more that the wine is going to be the worth, the better of more money you're going to bring in. On the other hand, this is a concave down function. So even though it's going to grow faster at first, it's going to grow slower later on. So what's going to happen is eventually the amount of growth on the wine is not going to be as good as the amount of growth you could get from just returning, investing it in whatever it is that you're investing that gets 5.75%. Probably the wine is growing faster than that percentage rate at the beginning, but slower than that later on. And so, as a percentage investment, and so anyway, we're going to try to figure out the optimal value here. So to do this, let's figure out what the present value of the wine is. So let V be the present value, V or B equals P, the present value. So the future value is P, the present value, times 1 plus 18 square root of T. So, but on the other hand, the value right now is, excuse me, the value total present value is f times e to the minus rt, okay, is the future value. And the future value then is p times 1 plus 18 square root of t times e to the rt, and that's going to be the value if we sell at time t, future value. So plug in the r, and we have this formula right here. Oh, man. Okay, continuing on here, we see that what we're wanting to do is we're going to maximize this value v. Well, this is actually a derivative problem, not an integral problem. And so we want to optimize a function. We want to take its derivative, set it equal to 0, and solve. So we just want to take the derivative of this function. We're going to, p is a constant. Okay, that's the amount per bottle now. And you're going to see that that's actually irrelevant. It's this other part that matters. And we're going to factor it out front and use the product rule. Actually, I'm going to think of it as part of this first part, it looks like, the way I did it, and use the product rule. So it's the first, p times 1 plus 18 square root of t times the derivative of this other part. Well, the derivative of this e to the u is e to the u times the derivative of the u is the minus 0.065. So that's the first times the derivative of the second, plus the second, e to the negative 0.065t times the derivative of the first, so still got a p. And the derivative of this, that's 18 times t to the 1/2, that's half of 18 is 9, t to the negative 1/2, which is 1 over square root of t. So we get that. This is p, not p of, but p times. I can factor out the p, and what's left, I can factor out the e to the negative 0.065, which I wrote as e to the positive 0.065 in the denominator. And I factored out a square root of t, so in the denominator. So that means I'm going to multiply this by square root of t. So where are we? Okay, so we got this here times 1 times square root of t. And we got the negative 0.065 times 18 is the negative 1.17. Square root of t times square root of t is just t. And then this one still has the 9, and that's it. Everything else is canceled out. So if you work out this, distribute this out together, you're going to get this up here. Now, that's the derivative. We want the derivative equal to 0. So this is equal to 0 when the numerator is 0, but not the denominator. P is not 0. This part down here, only place it's going to be 0 is if t is 0, which is not going to be an option for us. Well, I guess that's an endpoint, so we need to consider the value of just p if we put that in. Okay, if it might be better, not better to just get it, sell it right away. But in any event, we see when the numerator is 0, and so we do that right here, and we can let x be the square root of t, so x squared is t, and so this is this way right here, that t is x squared, that square root of t is x, and this is a quadratic equation, so we can use the quadratic formula here, plug in the appropriate numbers here, work it out, and we get x, so the square root of t is here, square both sides to get t, and of course t has to be positive, so this makes sense. So it's about 7.6 years, and we will get a higher future value at that point than you would at the beginning, because if you put in 7.5 in place of t here, you see the future value is bigger than just well, it should be bigger than just using p at that value. Okay, actually you should figure that out. But it turns out in this case that it's going to sell the wine when it reaches 7.6 years old is going to give you the best value. Okay, this is the last one I want to do today. Suppose that the income from a slot machine in a casino flows continuously in at a rate of f of t equals 620 e to the negative 0.02 times t minus 15 squared, where t is time in hours since the casino opened. If it's open 20 hours a day, what's the daily income? That would be from 0 to 20. would be the income for that day. And so this is what we get here. We just integrate that over the interval, because this is a flow rate times time, dollars per hour. DT is in hours. You get dollars out of this. So it's $4,800.67. Now this is one that the integrand right here doesn't actually have a nice antiderivative, so you really don't have any choice but to put this in the calculator. And there's the syntax for it in the calculator. Let's see if I can get pull that up to that page. There we go. And we will stop there, and next video we'll look at consumer and producer surplus. A little bit about supply and demand.